As additive manufacturing moves towards becoming a more mainstream production technology, materials will play a central role in enabling the performance, productivity, and technical compliance. For this episode of AM Infocast, we caught up with Sam Green, Principal Product Marketing 3D Systems, to discuss the evolution of materials of photopolymer 3D printing and how they are enabling production applications in diverse industry segments. Tune in to this episode to understand the latest material developments for photopolymer 3D printing. Welcome to AM Infocast, Sam. Thanks for joining us today. We've seen photopolymer 3D printing evolving considerably since its inception. Can you share some of the historical challenges and how they are being addressed to start off this conversation today?
Yes, sure. So photopolymers, as you've said, have served as the foundation of 3D printing for nearly 30 years now. Photopolymers, they're liquid polymer resins and they cure in UV light. So they are a type of thermoset plastic, different from thermoplastics like ABS or polypropylene or PC, which can be repeatedly melted and reformed into different shapes. Photopolymers, however, these are polymer chains and they're cross-linked and cured into a permanent form by UV light. So where traditional polymers are found in machined, cast, and molded plastic products, photopolymers have been typically used in 3D printing to what we say replicate or prototype the look and feel of those traditional plastics. So they're used typically for their aesthetic properties, but also for their overall versatility. So the printers, the materials together really deliver really good levels of part quality, accuracy, fine detail, resolution, speed, and all of that at a fairly reasonable entry price or range of entry price points, as well as fairly reasonable prices per part. So as a result of that versatility, you can find photopolymer 3D printing in a range of different applications and industries, whether it's consumer goods, focus group testing models, wind tunnel testing models for aircraft, to jewelry making industries, to heavy industries, where you need investment casting patterns. These advantages have historically come with some downsides too. Because those resins are initially cured in UV light, they remain susceptible to continued curing when they're exposed to natural UV light in real world conditions. So depending on the amount of sunlight and also other environmental factors such as humidity, 3D printed resin parts can degrade quite quickly once they're out of the printer. They can fade, they can turn brittle, and they can deform. Often you see clear parts turning yellow and then brown, for example. And as a result of this process, photopolymers have had some damage done to their reputation over the years, becoming labeled really as suitable for prototyping only. The question then becomes, so why not use other technologies? There's plenty of other additive technologies out there. Well, every technology in additive comes with its own basket of pros and cons too. So really a good solution maybe to try to add to the already good versatility that you get out of photopolymers by attempting to remedy their one weak point, which essentially is their long-term stability or their longevity. So how do we do that? So really, our chemists at 3D Systems, they took on the challenge of overcoming the long-term stability and performance issue of photopolymers. And they've really been able to revolutionize these capabilities with novel and patented chemistries not previously attainable with traditional resin materials. So these chemistries have opened the door to true production-ready polymers. So the figure 4 tough black 20 material was the first production-grade photopolymer that we formulated with this patented UV stability technology back in 2019. And since then, we've introduced a plethora of these materials, more than 10 or even as many as 15 production-grade materials that we have available today. And these materials are tested to demonstrate that they can retain most of their mechanical properties, such as their tensile strength and their modulus and their elongation at break and their notched impact strength. So they're tested to ensure that they can retain most of these mechanical properties over extended periods of time, typically up to 8 years in indoor conditions and between 1.5 and 2 years in outdoor conditions. So before the launch of our first production grade resins, our R&D teams evaluated the natural outdoor weathering decay process of several resin formulations over the course of an entire year. And these initial formulations represented really the breadth of the state-of-the-art chemistries at the time. And then at the same time, samples were subjected to what we attempted to create an accelerated weathering. So we ended up both with a natural and an accelerated mechanical and performance decay curve. And then you can compare the two, right? So we were able to develop an acceleration factor for outdoors and then also for indoor weathering. So now, as a result, all materials that we now push into development, particularly for our Figure 4 platform, they're now routinely naturally weathered to validate our overall process for reliability and accuracy. And they're also accelerated. They go through a process of accelerated weathering. And that's where we are today.
That's great insights on the challenges and how they are being addressed. How is this advancement in material development synergizing with the inherent advantages of projector based imaging?
Right. So, as we've sort of alluded to, there's been a sort of evolution over time for additive. Really, it began in the early days as simple fit and form prototyping. And then from there, it jumped into the realms of functional prototyping and then into indirect tooling. And now, really, the end game is direct production, right? So you're directly producing 3D printed parts that are relevant for production. So why is that important? So really, typically, there's a range of traditional manufacturing tools, whether it's injection molding, whether it's CNC, whether it's other tooling methods, and these provide really amazing value for production. But really, when it comes to large numbers of produced parts, typically, over 100,000 parts, and that's where you really get the value from traditional manufacturing. Where traditional manufacturing is not quite as strong is at the beginning of the product life cycle and towards the end of the product life cycle. So really, when we're talking about prototyping, functional prototyping, and then we move into low rates of initial production at the beginning of the product life cycle, and then at the end when we move towards obsolescence and spare parts. Any of those stages that are sort of either side of the comfort zone of traditional manufacturing, that's where additive can really add breadth and depth and agility and complexity to the traditional manufacturing process. So low to mid volume production, mass custom manufacturing, bridge manufacturing, and as I mentioned, low rates of initial production and the obsolescence part. So, 3D printing, it's always been there as a prototyping tool, and there's always been this challenge to really adapt it to the needs of true production. And in many instances, and with some certain technologies or vendors, it hasn't necessarily made that leap across the chasm from prototyping to production. So what does it really need in order to do that? So I'm setting the scene a little bit here because there's a few points that we need to build up to. The first is the fact that it's material chemistry, right? And we've talked about that just now. We've mentioned the fact that photopolymers have moved from being simple photopolymers to now production grade performance materials with long-term UV and humidity stability, both outdoor and indoor. So that's one aspect of what you need for true production. It's the material performance, the material chemistry. But the second major thing that you need is batch level productivity. And that's where the Figure 4 system really comes into its own. So the Figure 4 platform was introduced in 2018 by 3D Systems. Now, back 30 years ago, 3D Systems, as the inventor of the SLA, the stereolithography 3D printing technology, that uses a vector laser to scan and cure resins in a vat. Now, in contrast to that, the Figure 4 technology, while it still uses a vat, it replaces the laser with a projector-based imaging system. And that cures a whole layer of your part at a time, rather than point by point, which is what the SLA laser system uses. This projector that we use in the Figure 4 is relatively low power too, and it's easy to replace if it goes wrong. The other great advantage, of course, is speed. So the Figure 4 can print up to 65 millimeters per hour in the Z direction, for example. Now, there are a range of such projector-based printers on the market today. Many of them are labeled as DLP technology. However, Figure 4 uses a unique non-contact membrane, which means that the part, when it's being built, does not come into contact with the transparent layer at the bottom of the print tray. And this is unlike other what we call print and peel technologies that can be quite cheap and cost effective on the initial buy, but they can result in a slower and lower quality end part at the end of the day. The other great thing about Figure 4 is that it's a modular system, so you can add up to 23 additional print engines and create now a real a combination of high-speed printing and batch-level production capabilities, and you can scale that quite easily. The trick, of course, is to ensure that the parts off of the printer are suitable for production. The other great thing about Figure 4, which really enables us to turn to batch level productivity, as well as the speed, as well as the ability to scale the actual printers, is the software itself. So our 3D Sprint software has a number of production grade features that enable batch run productivity and efficiency. Our 3D Sprint software enables you to stack those parts that you're printing in an optimal form within the print chamber. You can automatically create your struts and supports. And by stacking those parts, you're able to print in batches of, let's say, tens up to 100 parts, if they're fairly small parts, in a single go. And you can reduce the time it takes to prepare that build by up to 80% of what it would normally take. And then once they're out of the printer, you have a very efficient post-processing workflow, which is quite automated, from cleaning to drying to curing to removing the supports, with the end result that you can actually produce many thousands of parts in just a number of 2 or 3 shifts over, let's say, the course of a working week. So just one example, when we were producing a number of parts for a show last year, we actually ended up producing over 4,000 parts, production capable, of course, production grade parts, 4,000 parts within 5 days using just 3 shifts and print jobs per day. So very, very productive. And that's the end game really, right? It's the ability to produce production grade parts, and many of them to really assist and support the traditional manufacturing process that we mentioned earlier.
That's great to see the recent development in material technology for projector based imaging. Can you share a few examples of materials enabling production applications?
Yes, sure. So as I mentioned earlier, we have a number of production grade materials. It's interesting because when we started this process, we introduced the Figure 4 back in 2018. We only came to market with actually 4 initial materials, and at the time, none of those were actually production grade materials. So it's interesting, between 2018 to 2019, when we introduced our first production grade resins, to now we're at the end of 2021, heading into 2022, we already have over 15 production grade resins, and they cover a range of capabilities, a range of different applications with some really unique mechanical performances and mechanical properties that answer unique application and industry needs. So for example, the Figure 4 rigid 140C black is the latest production grade material that we released at this year's Form Next. This is a long-lasting production grade material combining really high rigidity, high HDT, and together with high levels of toughness. So again, that was one of the traditional drawbacks of photopolymer resins, is that the higher the HDT, the more brittle these materials typically would become. So, in real under hood, for example, applications, in automotive applications, or real production applications, it's not enough to have a material with a high heat deflection temperature, or HDT. You also need these materials to have a good level of toughness and rigidity, so they can stand up to the vibrations and the knocks of real world conditions. And until now, really, photopolymers have had a really hard time delivering both on HDT and toughness. The Figure 4 rigid 140C black is one of our first materials that is really a 2-part material, and it actually solves this problem by providing an HDT of 140C along with good levels of rigidity and toughness that make it ideal for repeated snap fits, repeated friction contact, making it ideal for automotive underhood and electrical connector type components. So that's just one, but we have so many other materials. So, for example, we recently released the Figure 4 Tough 65C Black and the Tough 60C White. These are a little bit different. These are structural, load-bearing, production-grade materials, and they remain functional and environmentally stable for years. Again, as same as our other materials, up to 8 years indoor conditions and up to 1.5 years in outdoor conditions. These materials are great for handles, snap fits, brackets, anything that requires load bearing. The white version of this material also includes the biocompatibility ratings, ISO 109935 and 1099-310, that make them great for surgical parts, medical devices. We have a range of other production grade medical materials out there. So we have what's called the Med White 10, Med Amber 10. Both of those materials are again biocompatible, but they have 100 degrees C HDT, which makes them great for sterilization and autoclaving. We also have the rigid white material. This is a great material. It has a really bright, opaque white finish, probably the best opaque white material on the market today, according to many of our medical device customers. The great thing about this is that the whiteness, the bright whiteness, does not fade with time or does not fade after repeated sterilization and autoclaving, which is really important in the medical device sector. We have other materials such as the Tough Black 20, which is ideal for simulating ABS or polypropylene, great for parts that need good impact resistance and yet remain rigid, such as jigs, fixtures, or housings. And of course, we have the Pro Black 10, which is our best-selling, strong, rigid black material, great surface smoothness, really good first article success out of the printer, strong dimensional accuracy, and great dielectric properties, which makes it ideal for housings, casings, and other enclosures for circuit boards. And that material also features some thermoplastic type behavior, especially when you begin to chart the stress-strain curve of the material. So this material exhibits behavior such as necking a break rather than a straight fracture. And the advantage of this is that moving parts such as snap fits and buckle clips will be much more robust and useful for many more cycles than a typical resin material. And like all our Figure 4 production materials, they're all tested for industrial cleaning chemicals, detergent compatibility, automotive fluid compatibility. And another great point that I need to mention is that typical of resin photopolymers is that they exhibit excellent isotropic properties. So this allows users really a great deal of freedom to print their parts according to real needs and not just the limitations of the material and the printing technology. So you can actually set up the part and you can orient it in the print tray for optimal print quality, or you can orient it for the best speed or the best efficiency, or for minimal supports, or to support complex geometries or overhanging parts. And you can do all that without worrying about compromising the mechanical performance of the part because of how you've oriented it. So essentially the strength of that part, and that's what isotropic really comes down to, the isotropic properties, is that the strength of the part remains the same however you orient it and build it. And that's one of the great advantages when you combine the isotropic properties of resins now with our production grade chemistries. You really have a great 1-2 punch when it comes to efficiency and effectiveness of production grade parts.
Based on your experience in working in this industry, what does the future look like for photopolymer 3D printing technology and the materials?
Right, yes, good question. So I think, one of the first things that we can say about the future of production grade photopolymers is that they will continue to diversify in terms of their mechanical capabilities. And I think the other thing that we can say for sure is that the unique chemistries that we've created for projector-based imagery systems such as Figure 4, that we're learning and bringing these production-grade chemistries also to other platforms. So for example, we're able to bring now some of our production-grade material chemistries to our SLA platforms. As I mentioned earlier, the SLA was one of the original 3D printing technologies. It's one of the mainstays still today of large service bureaus. The SLA parts are still amazing in terms of the quality of the part, the surface aesthetics of these parts, the accuracy across all dimensions of these parts, the fact that you can create very large parts as well. The vector-based technology allows you to really scale and produce large one-to-one size parts that are needed for some of the big industries out there, such as white goods, such as fridges, freezers, microwaves, and also automotive and aerospace, UAVs, anything like that, where you need to efficiently and quickly create one-to-one scale, large, accurate, repeatable parts with good isotropic properties. Now, this July, it was actually the first time that we began to port over from our Figure 4 platform to our SLA platform some of these production grade resins. And we actually introduced the first production grade resin on SLA. It was called the Accurate AMX Rigid Black. This is a tough production grade resin material, ideal for repeatable high mechanical loads and structural parts. So it's also a long-lasting material, right? So like the Figure 4 production grade materials, this photopolymer is tested up to 8 years for indoor stability and 1.5 years for outdoor mechanical performance. And all of this according to the ASTM and ISO standards. This is something I probably should have mentioned earlier as well, that all of our production grade materials are tested according to the American Society of Testing and Materials, right? The ASTM standards. And this really provides, this enables us to really make strong claims that can be verified and tested. And these are not our tests, these are tests that are internationally recognized. So as I mentioned, the Accurate AMX Rigid Black is our first production capable resin for the large scale SLA platforms. And this provides all the proven advantages of SLA 3D printing, including the highest detail resolution, the great accuracy, the great surface quality, the great surface finish, comparable to traditional molding. But now you have all of that along with the longevity, the mechanical performance of those parts. So I believe that is the first step, right? The future, of course, is a combination of both, a combination of very high speed projector-based 3D printing based around platforms like the Figure 4 that enables you to create batch level runs, like let's say up to tens of thousands of small production grade parts quickly and efficiently. And in tandem with that, combined with that, complementary to that, you now have the ability to create one-to-one large parts, one-to-one scale large parts on the SLA platforms using these new production grade resins such as the Accurate AMX Rigid Black. The other point I wanted to mention, of course, is that we will continue to innovate rapidly. And you can see just the pace of resins has just skyrocketed for at least for 3D systems over the last few years. We have so many different materials now that cover the specific needs of various applications and various industries. And that is a direction we will continue to build on to answer the specific requirements of our customers' needs. Just some examples, we have a high temp 300 amber material. This is a material with a unique HDT, heat deflection temperature of over 300 degrees C, one of the highest performing HDTs in the industry. It's rigid, it's translucent, it makes it great for testing high temperature components, for HVAC, consumer appliances, motor enclosures, stators, and molds. You can use it to hold boiling liquids without any distortion to the material. So that's a great example of a material with a real use in functional testing and production requirements. Another great, very niche specific material is what we call the eggshell amber 10 material. This is essentially a sacrificial material, and it allows you to produce hollow parts with really smooth internal surfaces and detail resolution. And inside those parts, you can inject real silicone. And when it's ready, you crack open the 3D printed shell and take out the silicone part inside. So we have a whole range of different applications similar to these. So the eggshell amber 10, which is a sacrificial material, the high temp 300 amber. We have a number of elastomer materials. We have what's called the rubber black 10, which has a very high tear strength combined with a malleability and a Shore value of 95. So this is like a hard, strong, tear-resistant rubber. And in addition to that, we have another rubber 65A black, which is a more mid-level Shore value of 65A. excellent compression and rebound resilience, ideal for gaskets, seals, vibration dampeners, and such. So a whole range of different materials and innovations that we will continue to innovate on for different industries and of course for different scale, as I mentioned earlier.
Thank you for tuning in for this episode of AM Infocast. Stay tuned for the next episode next week.